I believe we left off last time at the very end of this on an example. And had we already done the conversion for P1? Okay, so all we really need to do is the second half of this question, is that right? Okay, great. And what we found for P1 at the end of last time was that it was something like 5, 306.9, 3 or something like that. Okay, so we were converting this here, which is Cartesian and XYZ, into cylindrical coordinates. So we used this table. We found Cartesian to cylindrical. If you want to go back to the table before this one, you can say, well, what are the variables in the cylindrical coordinate system? And you can see it's R, phi, and Z. And so if we want to get a point in the cylindrical coordinate system, we need an R, a phi, and a Z. So this is what allowed us to calculate that. Okay, second thing we want to do, we want to convert the vector A to cylindrical coordinates. So at the end of the day, you can say, well, what does a vector look like in cylindrical coordinates? And it looks like that. Okay, again, this can go right in your cheat sheet. Just shrink it down as much as you can so you save room. R hat, some A R component. Phi hat, some A phi component. Z hat, some A Z component. So at the end of the day, we should have A equals, and then we'll have R hat and some AR component, phi hat and some A phi component, and Z hat and some A Z component. So our job is to really find AR, A phi, A Z. So if we were to take this A and we wanted to break it down into AX, AY, and AZ, what would AX be? 2. Whenever you see these things, like whether it's AX, AY, AZ, or AR, A phi, AZ, what I want you to think about is just what's the stuff next to it. So for A phi, it's really what's the stuff next to phi hat. For AY, what's the stuff next to Y hat? So it'd be -3 here, right? So it's as simple as that. And so Z, the stuff next to Z hat, is 4. So we got a vector. We want to do this conversion. In order to do this, we need to find AR, A phi, and AZ. So we want to use that. That gives us AR, A phi, and AZ. So I'm just going to copy those down. So AR equals AX cos phi plus AY sine phi. Okay, so that's that one. The next one is minus AX sine phi plus AY cos phi. And the last one for AZ is nice and simple. Look at that. AZ equals AZ. So the AR, AX, that's 2. Nothing we can do with the cos phi. AY, well, I'm going to change that to be a minus 3 sine phi. Minus AX, that'll be -2 sine phi. And then again, -3, but cos phi AZ equals 4. So our total A is this uglier looking thing here. We've got R hat, and then we go, well, what's AR? That's what's next to the R hat. So it's 2 cos phi -3 sine phi. And then we have plus phi hat, but look, there's a minus and a minus. So I'm going to go minus phi hat, basically factoring out the -1. And then I'll make them positive inside. And then plus 4. So that's an ugly vector, right? That's much nicer in Cartesian coordinates, but there will be other vectors we see where it'd be much nicer in cylindrical coordinates than it would be in Cartesian, because this one's got the phi in it, because it depends on the value of phi. So for instance, if you wanted to evaluate it, so you could, if evaluated at P1, now we can plug in the values of P1, okay? This is R, which actually doesn't appear. Z doesn't appear, but the 306.9 for phi. You plug that there, 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 and there, and you just plug it into your calculator. Make sure you're in degree mode if you're using 306.9, and you'd get A equals like R hat 3.6 minus phi hat 0.2 plus Z hat 4. So like 3.6 would just be 2 times the cos of 306.9 degrees minus 3 times the sine of 306.9 degrees. And that's how you would do that. So you'll get more practice of these in the quizzes, all right? But I'll just be honest, I'm probably not gonna ask you on like a midterm or final, here's a point or a vector in cylindrical coordinates, convert it to spherical or something. I'm not gonna ask you a question like that. Could it be baked in? Yeah, it could be baked in as part of a bigger question, but maybe less likely than kind of the more fundamental stuff that we're trying to do with electric fields and magnetic fields and that sort of thing, okay? Okay, so let's get into some more interesting stuff. We're building up here. That was not all that exciting. Don't want to dive in, you know, into the deep end here. We're trying to build up. We're dealing with electric fields and magnetic fields. These fields are vectors. That's why we did a vector review. The types of fields we're going to deal with, sometimes it's nice to use Cartesian, but sometimes it's nice to use cylindrical and spherical. That's why we introduced the cylindrical and spherical coordinate system. Well, if we got these 3 coordinate systems, well, it'd be useful to be able to convert between them if we had to. So that's why we did that. Ultimately, we want to be able to talk about Maxwell's equations. Maxwell's equations describe all electromagnetic, classical electromagnetic phenomena. Maxwell's equations, well, they're dealing with vectors, so that's why we have to do that. They also have divergence and curl in them. Okay, so we got vectors, we got divergence, we got curl. So in order to talk about what Maxwell's equations mean and get some insight in them, and then we're going to simplify them and then do a bunch of stuff, we want to make sure we understand what divergence and curl and gradient too mean. So we're going to start with gradient. And my goal today is to, so you need to do some practice with these, okay? But the practice is, you know, kind of mechanically going through the things. And so examples take a long time in class, but they're really important. So I have a bunch of recorded examples. So you can speed me up or slow me down or stop me and take as much time as you want to actually, you know, turn the crank and actually, you know, plug numbers in and get something out of it, an actual answer. My goal today is going to be to try to give you a feeling of what these things mean, okay? Because that's what's tougher to get out of the textbook when you just have a bunch of equations, like a feeling for how to think about them and that sort of thing. And then I have, like I said, they're already available on the website, the examples of actually, you know, doing a real problem with it. So I'll talk a little bit about that, but we're going to start with gradient. All right. We are getting well into chapter 3. We are going to finish chapter 3 at maybe the first half of next class, something like that. And then we're in chapter 4 and chapter 5 the rest of the way. We'll cover almost all of chapter 4, but we definitely won't cover all of chapter 5. We'll maybe like half of chapter 5 or something like that. Okay. Gradient. So the things we're going to talk about: gradient, divergence, curl. When I say the word gradient, what do you think about? Like, forget about this class and stuff. When you just hear the word gradient, what do you think? Okay, topographical map. I like that. Anyone have anything different? Yeah, like a range of colors or something like that, right? I like both of those. Both of those are great. What you're really getting at with both those, it's like a range or a change, right? Topographical map will give the change in elevations. Maybe a gradient would give like a range of color. So really what I want you to think about is, how are things varying or changing? A gradient from here to there, how is it changing between two different places or something like that, okay? All right. We only do the gradient on scalars. What does that mean? Scalar is a number. It's a fancy name for just a number. Vector, that's a number with a direction. We don't do the gradient on the vector. So that's good. Scalars are easier, right? They don't have directions. And this is how you actually calculate it in the 3 coordinate systems. This is where you're actually like, you know, churning through a problem and you're gonna actually, you know, calculate a gradient, okay? So let me move ahead a little bit and then we're gonna circle back here. So here's the gradient. This is how you write the gradient. I'm never gonna write it grad T. I'm gonna use this upside down triangle next to a letter. Note that that is not bolded. It's italicized and not bolded. That tells you it's a scalar. Note that there is not a dot in between there, okay? When there's a dot between there, it's gonna be divergence. It's gonna be upside down triangle next to some scalar. You will describe that as the gradient of T. That's how you would say it in words, okay? So if I flip back here for a second and we just think about Cartesian, because I think it's nicest to think about things in Cartesian, and then you can go, okay, I can kind of see how it'd be the same in cylindrical and spherical. So think about things in terms of Cartesian. And let's talk about what this is for a second. X hat, Y hat, Z hat. At the end of the day, we end up with a vector. It's gonna have, at the end of the day, X hat multiplied by whatever this thing is, and Y hat by that thing, Z hat by that thing. We're doing partial derivatives. We're seeing how much something changes only with respect to X, and we're giving that the X direction, okay? So if I go ahead and I say, we got T, we have some T, and maybe it's a function of X, Y, and Z, like think it's got some like X squared and sine of, you know, 2y and plus 3z or something like that. It's got some X, Y's, and Z's in it. You would take the derivative with respect to X. What is the derivative with respect to X? How is it changing with respect to X? Okay. In other words, if you go along the X direction, how does it change? And we say that's how it's changing in the X direction. How's it changing the Y direction? That's Y, Z, that's Z. All right, so let's talk about what an example of what this could be. So the reason why T is used here is because temperature is a nice one to think about for this, okay? We got this room. Look at the floor. We've got these 1 foot by 1 foot tiles, right? So it's like 30 centimeters by 30 centimeters. It's got lines in between them, so it's a nice grid pattern on the floor, right? We consider this like the XY plane, maybe. This is the XY plane. You pick an origin of it. Where's a nice origin? Maybe that corner or something like that, right? Maybe X goes in one direction, Y goes in the other direction. Which one? Well, remember our right-hand rule, right? X cross Y has to equal Z. So when we define our Z and we define our X and Y, we have to make sure that that checks out. So maybe we make this X and this Y. So X cross Y equals Z, and Z's up. That's 0, 0, 0 right there. We can come over a certain number of tiles. If we come over like, I don't know, to like this point here, that's like 4 over 4 and X, 3 and Y if we're using units of tiles. Let's use units of tiles. All right. So it's like 4 by 3. And then if you're up here somewhere, maybe that's another like 4 or something like that. So I could split the whole room up into this grid in units of these tiles. They're all 1 foot. So it'd be like a 1 foot by 1 foot by 1 foot each cell. And at the vertices of each one of those, we have a position. And I could give you any number in here, like X equals 10, Y equals 20, Z equals 15, and you could go to that point in the room, right? Now imagine that we knew the temperature at each grid point, like everywhere we are at an intersection point here and then extend it up in 3 dimensions. I could go to this point in the room and say at this point, X equals, I don't know, 15, Y equals 5, 4 or 5, and Z equals 4 or something, 72 degrees Fahrenheit, okay? And maybe we have a function, a mathematical function, where you could plug in X, Y, and Z for the whole room, and it would spit out the temperature, okay? So now we got X, Y, and Z, we got some function, we're gonna call that T. That's our T, okay? So we have the temperature everywhere. We've got a window over here. Maybe imagine it's like earlier in the day and the sun's really shining in through there, and we got some air conditioning in here. I'm not sure where that's coming from. Imagine it's coming from this corner, all right, just to make it easier, because then we have the heat over there, and I guess we've got some vents up here. So yeah, maybe this is it. I guess it comes down from here, where all of these things are. What's that? Yeah, okay. So we got 6 of these that are cool air is coming down from. We maybe got the sun shining in and heat's coming in there, which is nice, because then you can imagine if it was just a closed off room, it's going to give us a really boring function of temperature throughout the whole thing. First of all, let's assume we had that room. We closed the whole thing off. It was an insulated room. It was the same temperature everywhere in the room. What do you think the gradient would be? Yeah. How is the temperature changing with X? How is the temperature changing with Y? How's the temperature changing with Z? If it's the same everywhere, it's not changing. The gradient would be 0, okay? We'd have no change. All right, so what we want to figure out by figuring out what the gradient is going back here to this thing that says it results in a vector. And then you might be like, well, that's weird. Temperature isn't a vector. So we're doing something to this thing when we calculate how it's changing that ends up in a vector. So by doing the partial derivatives, we're saying, how's it changing in X? How's it changing in Y? How's it changing in Z? The result is a vector that points in the direction of the maximum rate of change of temperature. So if you come, let's say, like here or something like that, you probably go towards the window, right? You probably wouldn't go that way if the sun's shining in and the heat's over there. So it results in a vector. A vector is a direct, it has a direction and it has a magnitude. The direction points in the direction of maximum increase in temperature. The magnitude tells you how much the temperature is increasing. It's an indication of that. Okay, so we end up, even though we had a scalar temperature to begin with, we end up with a vector that can tell us kind of the maximum increase and what that rate of increase is. All right, but then you might say, well, that's useful, right? For something, maybe you want to know how it changes. And another way you could think about this, instead of temperature, you could think about, maybe you have like a function, maybe it is like a large area of land that has different hills and valleys and that sort of thing, right? So the similar thing is, if you went to, and let's say you had an equation, a function that represented, you could give it like some XY coordinate on some XY plane, and the output would be the height of the elevation of the earth or something like that, right? And you went to some position and you calculated the gradient. The result would tell you, which way should I walk so I go uphill most rapidly? And how quickly, the magnitude would tell you, how quickly am I going uphill? Okay. All right, so that can be useful because it can tell you what we're going to deal with as electric and magnetic fields. So we're going to be able to tell something about the fields. Yeah, go ahead. Yeah. Then always start at the origin. So we're gonna calculate a gradient, and then you can evaluate it anywhere in the room. So if you come over here, you could get a totally different vector than you would over where you are, because who knows what's going on with the way the temperature is. So good question. So that would just be a relative coordinate system we set in the corner so that we can reference everything from that point. But then we would evaluate the gradient based on the function that defines the temperature everywhere. T is a function of X, Y, and Z, so we can stick in any X, Y, and Z in here and it'll spit out the temperature. We do the gradient on that function, but then we can evaluate it anywhere in here. And when we evaluated it over there, it will give you what the vector, magnitude, and direction is at that point, but it could be different at all the different points in the room. Okay, so that tells you the maximum rate of change and the direction. But what if you asked yourself a question that was more like, all right, I'm at this point here, maybe I've calculated my gradient and it says it's directly towards the window and it's giving me some amount that it's increasing in that direction. But I didn't want to know, how it's changing maximally. I wanted to know something different. I wanted to know how much is it changing in the Y direction. So we would still calculate the full gradient, just like we talked about, but then we do a dot product with a unit vector in the direction that you're interested in. It's like the component. You could think about it as like, okay, my maximum rate of change is over here. I want to know how it's changing in this way, okay? And so I'll do the dot product of the gradient with a unit vector in the direction that you're interested in. Yeah. Okay, so I don't think we're going to use these properties too much. The first one is what you would expect, the gradient of the sum of two scalar functions. You can just kind of do the gradient of u plus the gradient of v. This one, maybe not so expected. Maybe this one as well. I don't think we're going to use those, but they are just two properties of a few properties of the gradient. So don't worry about those too much. Okay, here's where I kick in. I've already posted this example, but I just want to talk about it a little bit. We're given a function V, thinking voltage, because you can have a electric potential throughout the room, just like instead of temperature. And it's a function of X, Y, and Z. So you could plug in any X, Y, and Z value, and it would spit out a V, just like we could plug in any X, Y, and Z and spit out a temperature, right? So the first thing you're going to do when you do these things is think, what coordinate system am I in? This one, it's fairly obvious. And then you go, all right, I'm trying to find the gradient. So I'd come back here and I'd go gradient, Cartesian coordinate system. This is the one I have to use. So the first part of this is x hat partial derivative. Note that d, it's like a backward 6 or like a really curly d, means partial. What does partial mean? Well, we have a function of x, y, and z, but we're only taking the derivative with respect to x. So it's partial. If we had a function that only had x in it, and then we took the derivative with respect to x, that'd be a full regular old derivative with a regular old d. But because we're doing partials, we do the curly one, okay? So to figure out the first part of this, x hat partial derivative with respect to x. So we would do it one by one here. And so what would the partial derivative with respect to x of just the underlying part be? Yes. So it'd be 2xy, right? What about this one? Just be y squared, right? And this one, z squared. So that would, whatever that was, next to it would be x hat, right? We just did that, and then you stick an x hat next to it. Next one, y hat partial derivative with respect to y. What would it be? Yep, 2xy, 2yx, 0. Okay, that would be next to y hat. Last one, derivative, partial derivative with respect to z. Yep, 2xz. Then, so that's basically all that I did in the recorded video. Once you get that, now you stick in 1 minus 1, 2. Everywhere that there's an x, you plug in 1. Everywhere where there's a y, you plug in minus 1. Everywhere where there's a z, you plug in 2. So that's that example. Next example, also already posted on Canvas. I take my sweet time with this one, I think, on Canvas, just because it's, well, what coordinate system is it? Yeah, cylindrical. So identify it first. How would you do that? Lowercase r, z, and phi. Those are the three variables in the cylindrical coordinate system. Find the directional derivative of that along this direction and evaluate it at that. So this one's a little more involved. But remember, directional derivative, the first thing we have to do with it is to just calculate the regular old gradient. You'd come here and you go, oh, but I'm in the cylindrical coordinate system. So you would need to do this first. You need to go, all right, r hat, and then the partial derivative with respect to r. What would that be? Yeah. So the r squared, all this stuff here, all that junk is just constant with respect to r, right? So this could be the same as like 2r. What's the derivative of 2r with respect to r? It's just 2. So all that would be left is just z squared cos 2 phi. That would be the partial derivative with respect to r. And so then we would just go r hat and then that. Then we do the same thing. The only difference here, just be careful. You do the partial derivative with respect to phi first, then you divide by r. And then that's the phi hat stuff. Okay, the z is fine. You just do the same thing, partial derivative with respect to z. So that would just be like 2rz cos 2 phi, right? All right, so then that gives you the gradient of v, but it wants the directional derivative. It says, how is the gradient of v changing along whatever this is? To do this, we have to get the unit vector for this first. Do you remember how you get a unit vector from a vector? You divide it by the magnitude. What would the magnitude of that be? Yep. Square rooted, right? So there we go. So it'd be 2 squared 4 plus 1 squared 1. So it'd be square root of 5. So we would divide that by the square root of 5. That would give us our like a hat, if you like. It would have an r hat component and a z hat component. We would then do the dot product with the result of our gradient. Okay. Then we have to evaluate it at this point, and you can safely assume that this point is given to you in cylindrical coordinates. Why? Well, the whole thing's in cylindrical coordinates for one, but number two, we've got a number and then we got a pi here, and then we got a number. It's an indication. It's not definitely, like it's not like 100% sure that that means that the middle one's an angle, but it's a pretty good indication that that one's an angle. And if that one's just a non-angle and that one's an angle and that one's not an angle, that implies a cylindrical coordinate system because it's r phi z. It's always written that way, r phi, so the angle's in the middle. If it was cylindrical, if it was spherical, then you would expect more like a number and then angle, angle. Okay. All right. So this whole thing is worked out in detail, recorded on Canvas. So with that, then, that's the gradient. We'll use the gradient a little bit, but we're going to use divergence more than the gradient. Okay, so let's talk about divergence. The picture at the right here is a point charge plus Q. And the black arrows represent the field lines pointing away from it. So positive charge always has electric field lines pointing directly away, and that's in all directions. So it'd be coming out towards you, it'd be going into the board, it'd be going out in all directions. If it was a negative charge, like a negative Q, it would be pointing in all directions, okay? Divergence is gonna give us a way to determine whether something is acting like a source of field lines, kind of like the positive one, where the field lines are emanating from it, or if it's acting like a sink of field lines, all the field lines are terminating at it, kind of like the negative Q. That's what we're going to do. Okay. Now, in order to talk about this, we first want to talk about flux. You probably heard the term flux before, maybe in like physics 220B or equivalent or whatever. So we want to talk about flux for a little bit. When I say flux, you can think flow, okay? So how something's flowing. If you want to visualize something maybe a little easier than electric fields and magnetic fields, you could visualize water or air, like a fluid flow, okay? Flux density, the amount of outward flux or the outward flow crossing some surface boundary. So imagine you had some, what would be a good example? You could think of air, maybe. Imagine your surface doesn't affect it though, okay? So maybe you have like, maybe you had flowing water and you had like a fishing net or something like that in the river. And so your fishing net, if you considered that to be like the surface, the water would flow through it, right? If you considered your surface to be the surface of that fishing net, that wouldn't be a closed surface, it'd be an open surface. And pretty soon we're going to make sure the surface is closed. But just to give you an idea of it, you wouldn't really be disrupting the flow of water that much. You would just, and if you think of a fishing net, it's kind of broken up into little pieces, right? In between the grid pattern, I guess. That's where the water would flow through. And so you could kind of measure how much water is flowing through each one of those. And then you could think, well, what does each one of those represent? You'd say, well, if we consider each one, the hole in between in your fishing net, that could represent your DS, your differential surface area. You had some kind of a semi-spherical, imagine your fishing net when water's going through it, it opens up and it's perfectly half of a sphere, okay? Then you consider the lines on the fishing net to be essentially splitting up the different surfaces, the subsurfaces that make up the half of a sphere, and we'd call those DF, our differential surface areas. And then if we could somehow measure how much water flows through each one of those, okay? By doing that, we could get a measure of how much water is flowing through the entire surface of the net. Okay. All right, so what do we got? Flux density of E. E is our electric field, but in that example, it's like the water, okay? So that's like the water. Dot ds, what's ds? Well, those are those little squares, the holes in the net that the water's flowing through. Ah, but that's a bolded S. That's a bolded S, it's a vector. So then we have to think, well, what's the direction of that vector? We said it represents the holes in the fishing net where the water's flowing through. Do you remember what direction we said surface areas have, or DS has? We're gonna always have our DS be perpendicular. It's perpendicular to the surface itself. It's the normal. So in this case, we've got one positive point charge and our surface is a complete sphere. That's the green thing. Considering one DS, and the normal to that is n hat, okay? Okay, so that's our DS. The magnitude of it is the actual area of that square. The direction of it is normal to the surface at that point, which would be different, right? Like if you considered a point down here, the normal would be something like that. In our fishing net, if it's like this, the normal right in the middle is maybe right down river, but at the sides, the normal is going to be off to the side, right? Okay, so what can we do? Well, this ds, it's got a magnitude and a direction, right? ds, it's a vector. Well, it up here is saying the direction is n hat. And its magnitude is just some ds, but note that I'm not writing the arrow over that s, because that's just saying it's its magnitude. That lets us go from here to there, which is nice because then the DS's cancel out and you're just left with E dot n hat. The reason why you divide by this is it's like, well, imagine you're considering a bigger chunk, a bigger square, your DS is bigger, your magnitude of that area is bigger. Well, obviously more water is going to flow through it. So by dividing by it, you normalize that out. That's why we have a density here. But where we really want to go is here, to total flux. All right, total flux. Now we got an integral sign. Does anyone remember what that circle in the middle of the integral sign means? Oh, I like that. People remember that well. Okay, great. So it's a closed integral. We are going to deal with line integrals that are closed and surface integrals that are closed. This one's a surface integral. We got S and we got a ds. That means it's a closed surface. So it's not our fishing net that has its opening where the fish will go into, right, and the water goes into. It's completely closed off. Because we want to, if we want to calculate the total flux, we have to know it over an entire surface. In that case, you know, we're only covering half the potential surface area, and it wouldn't tell us the total flux. It would only tell us the flux over that particular surface. The total flux tells us, kind of like this sphere does up here, how much, in this case, it's acting like a source overall. Whereas if we, you can imagine if we only considered like the top half of this or something, and we didn't know, maybe it's not just a plus Q, maybe it's something much more complicated in there. We don't know what's going on down here. And ultimately where we're heading is this surface. We are going to shrink down to be basically like a point. And so we want to know what's happening. Is it overall, is it acting like a source or a sink of fields? Okay, total flux. How much of the E field is going through this surface S? We have some surface S, it's a closed surface. It doesn't matter what shape it is. It's easiest to think about it as maybe a sphere or something. We have some surface, it's closed. We split it up into little pieces ds. Then we do E dot ds. You remember what I said to think about when we have the dot product? It's like, it gives you an indication of how aligned two vectors are. Well, that plus Q there, the fields go away from it in all directions. So the field, if it was drawn there, would be pretty much like that. Very much, it'd be perfectly aligned with the n hat. So for that ds vector, if we did E dot ds, it's going to give us a maximum, because think of what's in the dot product. There's the cos of the angle between the vectors. Cos of 0 is 1. If it wasn't this point charge and it was some other thing, maybe we were thinking about a magnetic field or something, and the field at this point was actually perpendicular. Exactly, it'd be 0. Nothing is no field lines are actually flowing through the ds. So it'd be 0. If it's something in between, it's the dot product. It's telling you how aligned they are, the cos of the angle between them. Okay. All right. So now let's imagine a cube. This is a bit of a weird example, but it's the simplest one where you can get a sense of where the equation comes from. We have some electric field E. We have some cube. It's delta X by delta Y by delta Z. The electric field is represented as some generic field going through it in the green arrows. And it could be anything. That's what that representation of an electric field means. It's got some X component, it's got some Y component, it's got some Z component. It doesn't really tell you anything, but it's the most generic case, because any field could be represented as having some X component, some Y component, and some Z component. And so if we take into account the field, the flux going through all 6 sides of this cube, what we've done is we've calculated the total flux. So we said here it has to be a closed surface. A cube is a closed surface, right? But there's nothing wrong with splitting that closed surface up into its individual pieces that together all comprise a closed surface. So if we split it up into its 6 faces and figure out what E dot ds is for each one of those faces individually and add them all together, overall, we have done the closed surface. So that's what we want to do here. And so to start with, we can say, well, let's start with face one, okay? Face one or flux one, okay? And so if we did this, we are over here on this face one. And so what would we do? Well, we need to do some integral over face one, and it needs to be of E dot ds. And then we can say, well, what is ds for that? Well, we know ds has a direction, it has a magnitude. The direction is normal to face one if we're dealing with face one. So it's going to be n1 hat. And its magnitude is just going to be a ds. So really what we're doing here is it's like we've kind of like split this up into pieces, right? The whole thing, the whole face. Each one of these is a ds. And so if we're, splitting up into tiny little pieces, then what would our ds be? Well, it's going to be an area. So it's going to be a length times a width. Everywhere on face one, so look at your coordinate system here. Everywhere on face one is at the same value of x. So you could say, well, we have some distance there and we have some height there. So you have to look at the coordinate system and say, well, what is that? And say, oh, that's z. And what is that one? What is the height? Oh, that's y. So if it's a ds, it's a differential area. So ds would be dy times dz. Okay, so then we can go equals integral face one. E, we have an expression for E, x hat ex plus y hat ey plus z hat ez. And then we need to do the dot product with n1 hat. And what direction is n1 hat with respect to our coordinate system here? Yep, negative x hat. And we said our ds is dy dz because we're doing basically, length times width. Okay, now we got to do this dot product. So we got to do the dot product of that one and that one and that one. So what would the dot product, let's start with this one, y hat ey dot minus x hat. 0, because they're perpendicular. X hat, y hat perpendicular. Boom, 0. What about this one? Also 0, because we have a minus x hat dot z hat. They're 90 degrees. X and y and z are all 90 degrees apart from each other. Minus x hat dot x hat. Minus 1. Okay. So we have minus 1 there. And then we have, so what we're really left with here, let me do this intermediate step. Face 1. We have minus 1 minus ex dy dz. Okay. Now we're going to simplify something. We're saying this is a small differential cube. So we're going to say the electric field doesn't vary that much across this face. Okay. And if it doesn't vary that much across that face, then basically we can treat this as a constant and bring it outside the integral. And we can say we're going to approximate it as whatever the value of ex is at the center. So I'll say approximately equal to ex at 1, meaning the value of the electric field in the x direction right at the center of face 1. And then you can say, well, what about dy dz? Well, we've taken the ex out, and now we've only got the integral of dy and dz. So if you think about dy for a second, you do the integral of dy, it would just be y. And then you have to plug in the limits of integration. So what's y? Y is up, okay? And so when you plugged in the limits of integration, you'd plug in the starting and ending points and subtract them. You just end up with delta y, okay? So all of that just comes down to delta y, delta z. where ex at 1, and we should have a minus sign here because it comes from that minus sign there. Ex at 1 is the value of ex at the center of face 1. All right. What if we did face 2? What would change about that, do you think? Exactly. So the only thing, if we considered face 2, the only thing different is its n2 hat, which is in the positive x hat direction. That would make that a positive x hat, which makes that positive. And we'd be dealing with the center of face 2. So let me write that down. So we'll just say F2 equals EX2 delta Y delta Z. And we could also write another equation for let's do EX at 2, okay, this thing there. We can say EX at 2, if we start with EX at 1, let's remind ourselves what EX at 1 is. There's some electric field going through this cube. We don't know what it is. But we're saying we know what it is roughly at that point. Overall, it could be doing anything through this cube. We're approximating it to be at the center of that point as EX1. If we wanted to write the EX2 in terms of its value at EX1, we could start with EX1 and then say EX1 plus the electric field changes somehow in the x direction, and we go a distance delta x away. So basically what we're saying is we want another expression for the field here. If we know what it is here, we can say we'll start here. If we know how the field changes in the x direction, we can say that change this far because that distance is delta x. Okay. Don't worry about if you couldn't reproduce this. We're just building up to what the definition of divergence is. Question? Yeah, it looks like a 2, but it's partial derivative. Yeah, sorry about that. Okay, so then we could plug this into there. Because this is EX2. So if we plug that into there, we get F2 equals that whole thing, EX1 plus partial derivative of EX divided by X, delta X, delta Y, delta Z. Now let me expand that. I'm just going to multiply the delta Y, delta Z through. So we get EX1, delta Y, delta Z, plus partial derivative EX, vector X, delta Y, delta Z. If I did F1 plus F2, look at this term right there. EX at 1, delta Y, delta Z, minus EX at 1, delta Y, delta Z. If I add them together, those two cancel each other out, and we're just left with the rest. What is delta X, delta Y, delta Z? That's the volume. Length times width times height. If we did F3 plus F4 and F5 plus F6, we'd get something very similar. We'd get partial derivative EY with respect to Y, delta X, delta Y, delta Z, and partial derivative EZ with respect to Z, delta X, delta Y, delta Z. Now, if we wanted to get the total flux, it has to be over a closed surface, which means it has to be F1 plus F2 plus F3 plus F4 plus F5 plus F6, because there's 6 surfaces of the cube that make it a closed surface. So we'd have to add all of these together. Note that they all have the delta x, delta y, delta z in them. So that could be factored out, and you'd just be left with partial derivative of x with respect to x, partial derivative of ey with respect to y, partial derivative of dz with respect to z. Okay. This is what we are going to call divergence, and this is delta v. And it's a generic, even though we did it for that particular cube, that is our generic divergence. I'm not going to write it this way with div e though. One thing before we go on, we want to shrink this volume down to 0. And what that does is it essentially approaches a point. So we can evaluate the divergence at a point. Okay. Here is the formal definition, which fortunately you will never probably have to use. Okay. So this is basically takes the total flux and then it shrinks the volume down to 0. And that's the formal definition. The one that we're actually going to use is that one. This is what we're actually going to use, and I will not write it that way. I'll write it that way. When you see it, we got upside down triangle dot E. The way you say that is the divergence of E, or the divergence of the electric field. Don't say like nabla dot E or something like that. Just go divergence of E. Yeah. Yeah. Back to here. Yeah, no problem. Divergence of E. Good. Okay. Divergence. So remember, gradient had to be scalar. We talked about temperature. We talked about like height. No, we don't do the gradient of vectors. The opposite for divergence. We have to do it on vectors. Okay. So always operates on vectors. The result is a scalar. That scalar tells you, is it acting as a source of field lines or is it acting as a sink of field lines? If you get a positive number, that means it's a source. If you get a negative number, that means it's acting like a sink. Okay. If you get 0 for the divergence, it's divergence-less. It's like a uniform field passing through. It doesn't act as a source or a sink. Okay. This is the divergence in the Cartesian coordinate system. That would be described as the divergence of A. These are a little uglier. Okay. Same thing, but in cylindrical or spherical. A couple things I want to point to here. Let's take the ugliest one. What's the ugliest one? Spherical, and maybe the middle one. That one's pretty ugly, right? So how would you do this? Well, you need to know the vector A. Okay. And if you knew A, well, if you're using this one, you're probably in spherical coordinates. From what we did at the beginning of today, you could convert to spherical coordinates if you weren't, but let's assume we're in spherical coordinates. If we're in spherical coordinates, we know there's a capital R hat, a theta hat, and a phi hat. Remember what I said at the beginning, the components A theta means the stuff next to theta hat in the representation of the vector. So you go, what's the stuff next to theta hat? And I recommend you break these down into smaller steps rather than try to do this all at once. So if you were given the vector A in spherical coordinates, the first thing I would do is I would probably write down A capital R equals blah, blah, blah. A theta equals blah, blah, blah. A phi equals blah, blah, blah. If I was trying to evaluate this part of it, I would go, all right, what's the next thing I have to do? Respect the brackets. So the first thing I have to do is multiply A theta by sine theta. Okay. Then the result of that, I take the derivative of with respect to theta. The result of that, I divide by r sine theta. Okay. And that gives you that middle piece. Over here, you'd say, what's next to the capital R hat? That's AR. Multiply it by R squared, then take the partial derivative with respect to R, then divide it by R squared. So just take it one step at a time, because it's easy if you're trying to do it all at once to make a mistake. For cylindrical, it's not so bad. Again, just here, you got to multiply by the R first before you take the partial derivative. Just exactly. Trust how it's written. Just follow the parentheses and you'll be okay. And break it down into small steps. All right. What do we got for time? We got 15 minutes. I'm going to talk about that at the end. Let's talk about the examples for a second here. Again, these are already recorded. I think it's like a 20-minute video or something like that of me going through these two examples. But let's do like what we did with the other one. Just kind of talk about it, and then you can grind through it. So you would look at this. First of all, check out the example in the text 311. That's a good one. We are being asked to find this thing. Now, you need to know what that is, because I could, on midterm 2, say, in words, find the divergence of A. Or I could just write it like that, and you would need to know what's up. Okay, first thing as usual, identify your coordinate system. What coordinate system are we in? Exactly. So just don't get thrown off by the signs and the E's and stuff like that. The function is in terms of X, Y, and Z. There's no R, thetas, phi's, any of that, right? It's X, Y, and Z. That means it's Cartesian. You'd go, okay, it's asking me to find the divergence of something in Cartesian coordinates. I'm going to go to my formula. I got to do this. I need to identify my AX, my AY, and my AZ. What would my AX be? Is that all? Just remember, you got to multiply that through, right? Remember, AX is all the junk next to X hat, but that one's next to both of them. So AX is the stuff next to X hat, so it'd be sine 2X, but it would also be e to the minus 2y. What would AY be? Yep. So what would the partial derivative of AY with respect to Y be? So it'd be negative. So you basically, if AY is cos 2x times e to the minus 2y, right? We're taking the partial derivative with respect to y. This has got no y in it. That's just constant. We only have to worry about the partial derivative of that with respect to y. Negative 2 would come down front, right? Because that's a derivative of minus 2y, and that would stay the same. Times cosine, exactly. So the partial derivative of AY with respect to y would be minus 2 e to the minus 2y cos 2x. If that's a lot for you, I go through it slowly in the video. So you do that for every each one of them. What's AZ? 0. So that part's easy, right? So if you come back here to the equation, the third AZ is 0, so that's not even there. Okay. And that's that. That's that one. Okay. Another one. This one again, already recorded, post on campus. Step 1, identify your coordinate system. Which one are we in? Cylindrical. How do you know that? Well, we've got R hat, phi hat, and Z hat. That is the cylindrical coordinate system. This time we not only have to find the divergence, but then we have to evaluate it at a particular point. That's what this says. When it says find it at this, you find it, then you plug in the numbers at that point. That's what that means. That's a good question. So if you got this on an exam, it would be totally fair game to just ask me. For your quizzes and for this, if it's giving you something in cylindrical, you're safe to assume that the point's in cylindrical, but definitely something that would cross your mind, because the middle one here is the one that would normally be an angle, right? If it's cylindrical, and it's 0. So 0 could be an angle or it could not be. And if it's Cartesian, then it's like, oh, now do I have to convert that point first or something? Normally that won't be the case, unless it explicitly told you. Like it would say, it'd be dirty. It would be dirty for me to do that, but it was like, find the divergence of A at Cartesian coordinates point 2, 0, 3, right? If it's like this, you can assume it's cylindrical, which means it's R phi Z, okay? It's always written that way. Just like it's always written X comma Y comma Z, in cylindrical, it's always gonna be written R comma phi comma Z, and in spherical, it's gonna be written capital R comma theta comma phi, I think is how that one's written. Okay, what do we got to do? Well, you first identify it's cylindrical, pop back. Cylindrical, divergence, boom, I've got a formula on my formula sheet. What's in this thing? Well, we need to know what AR, A phi, and AZ are. So, okay, so let's go back to it. AR, A phi, and AZ. What would AR be? R cos phi, it's the junk next to R hat, right? What would A phi be? R sine phi, and AZ, 3Z. All right, so we have all those. Then we'd come back here, we look at this and we go, well, the R component, we actually have to multiply by R first. So it'd be R squared, and then take the derivative with respect to R. So it'd be 2R cos phi, okay? So you work through that for the whole thing, and you get some solution, right? Like that one was like 2R cos phi. That would be the first part. Yeah, right. So we still have to divide by the 1 over R. Exactly. Yep. And then we would need to plug in the phi, which would just be cos of 0. So it'd be 1. And so that would be the first part of that. And so you do that same thing with each of them. So take your time watching the video with this. I go slowly through all this. You can pause me. If it seems easy, you can speed me up. Just adjust it like that, but they're already up there. It's under the recorded lectures part of it. It says like gradient examples and divergence examples. Okay. Okay, so the last thing I want to talk about tonight, we got 8 minutes, is the divergence theorem. All right. This thing is used all over the place in electromagnetics. And I want to give you a feel of what this thing means. This is one of those cases where you see an equation like this in the textbook, and you might be like, okay, like, all right, that's, it's a bunch of, maybe you buy it, you're like, okay, but it might be difficult to kind of get a feeling for what it means. So I'm going to try to sell you on why the left-hand side of this equation equals the right-hand side of the equation. All right, so let's break it down here. All right, left-hand side of the equation. Well, we've got an integral sign, right? So it's an integral, so that's disappointing already, maybe. It's a volume integral. And you look over and you see dv. When you see an integral, what you can think is, I got something, in this case a volume. I'm going to break that volume up into a whole bunch of tiny volumes. I'm going to figure out what the effect is of this thing in each of these tiny volumes. And I'm going to add them all up or integrate them to take into account all of those little volumes that make up the big volume. All right. So what's the easiest volume to think about? Let's think about a balloon. So I blow up a balloon, I tie it off, it's filled with air. It's got a very thin surface, right? Imagine it's like a red balloon and I've got a black marker, okay? I'm not going to use the black marker yet, but I've got it. Then I go inside the balloon where the air is, and I break it up into a ton of tiny little cubes, let's say, okay? And for each one of those tiny little cubes, I do the divergence of E. So then you go, okay, I'm going to think about one of those tiny cubes. And then I think, what does divergence mean? And we go, oh, divergence, how something is diverging. Is it acting like a source or a sink? So I'm going to look at that tiny little cube, which goes down to approaching a point, right? And I'm going to say there, at that in that tiny little volume, that tiny little delta V, that tiny little dV, is it acting like a source or a sink there? It's going to give me a number. Remember, the number represents how much fields are emanating or sinking into that point. Then I go to the next little cube, maybe next door, and I do the same thing. And the next one, and I do the same thing. And maybe on some of those, it's acting like a source, right? It's emanating from it a lot. But then in other areas in our balloon, in the air inside our balloon, it's actually acting as a sink. Okay. And so in some places it's being like a source, in some places it's being like a sink. And we are adding, it's like the net effect, right, of all of those that make up the total balloon. So when I integrate all of those together, the overall net result is how much this entire volume is either acting like a source or a sink of the fields. Okay. That's the left-hand side. The right-hand side, got another integral, and this one's worse because it's got the circle in the middle, right? That means it's a closed surface. It's also got the S to say surface, and it's got a DS. All these things are screaming surface, and the circle tells you closed surface. That's not just any closed surface. This equation, this divergence theorem, only works if that surface S is the surface of the balloon. It's the surface that encompasses the volume on the left-hand side. So rather than talking about the little cubes of air that make up the volume inside the balloon, now we're talking about only the red surface of the balloon. Okay. And what are we doing? We're splitting it up into little pieces. I got my black marker. I'm drawing little squares all over it, like a checker pattern all over the balloon. Okay. I'm looking at each one of those DS's. DS is an area now, right? It's a tiny little area. It's got a direction. That S is bolded. The V is not bolded. That doesn't, we don't really have a volume with a direction. It's just not, it doesn't make sense. You might say, well, surface with a direction doesn't make sense either, but we've given it a direction. We've defined it to have a direction. And what is that direction? It's perpendicular. So for every little black square that I've drawn on the surface of the balloon, the normal to it is directly away from it. Okay. So you pick one of those black squares, one of those DS's, and then you do E dot DS for it. If the electric field is perpendicular to that normal, to your surface, it's not going through the surface. So it would have zero contribution to that integral. If it's perfectly aligned and it's going right outside of the DS, it'll give you a maximum. If it's somewhere in between, it'll give you some contribution to fields going outside through the surface, but it won't be a maximum. Then we take into account all of those little surfaces. We do that for each one of them. And you're like, well, at some places, it's going like directly out of the surface. In other places, it might be going into the surface, right? So when we integrate over the entire surface, what do we end up getting? We end up getting an overall net effect of how much of the fields are going through the surface or into the surface. So that's why they're equal, because on the left-hand side, we broke it up into volumes and we said, how much is it like emanating or sinking into each one of these volumes that make up the whole thing? The right-hand side says, we're just gonna look at the surface because everything has to go through that surface or into that surface. And that's why they're equal to each other. And why is this useful? It's useful because sometimes, especially if you go on and take 571, you'll have some equation and it's really nice to be able to switch between a volume integral and a surface integral. Like if you're one side of the equation, maybe you have a different right-hand side of this equation, right? It's something totally different, but it happens to be a surface integral, not of E dot ds, but something different. So you have a surface integral of ds on this side, but you've got a volume integral on that side. You can use the divergence theorem, swap it out so that it's a surface integral too. Now you have a surface integral on both sides, and you can like ignore the surface integral in some cases because it's the same surface integral. So it can simplify things a lot. Okay, so any questions about that? We won't use the divergence theorem too much, but it's super important in electromagnetic, so I wanted to spend some time on it. And if you went on to 571, you definitely will see this. Again, it's one of the things that kind of keep coming up. All right, so we have less than a minute to go. I'm not going to start anything else. We're going to come back on Wednesday, we are going to learn about the curl and the Laplacian. Look out, I'm going to post in the announcements 2 YouTube videos that are really good. I don't know if you've ever heard of like, I forget what it is. It's like 2 brown, 1 blue or something like that. Anybody heard of that? Yeah, he is awesome. And so he has a video on divergence and curl, really good, and another one on gradient and the Laplacian. So I'm going to post that as a link in the announcements. Watch, it'll give you a better feel for it. We'll come back, we'll cover curl, and then we're actually into chapter 4, electric fields, and then going on from there. Okay? All right. So I'll see you all on Wednesday.